Hi, I am Muhammad Sajid Zahur. Today we will discuss about linear operators, and we will define some or we will discuss some linear operators like integral operator and differential operator, and also we will discuss the addition and the scalar multiplication of a linear operator. And in this lecture we will also discuss some definitions or like kernel and image of a linear operator. So now we will start with the concept and definition of linear operator. Here first, in order to define the linear operator, first we will take the two vector spaces, and the first vector spaces is denoted by V and the second vector spaces is denoted by W, and we will define these two vector spaces on some same scalar field K. Okay, now we will define a mapping. We will define a mapping L from a vector space V to vector space W, and we said that this linear mapping or this mapping is linear if the following conditions are hold. In order to define any mapping, or in order to set any mapping is linear, we will prove these three conditions. Okay, the first condition is that when we take the two vectors from the domain vector space, this is this vector space V, and first we will add these two vectors and we apply the and we will apply the operator L from this sum. Then this will becomes L of V1 plus L of V2, or simply we say that this linear operator is applied separately of each of the vector. Okay, this is our first condition of the linear operator. And in second condition, this is the scalar multiplication, and in which condition, if we will multiply some vector by some scalar alpha, then this scalar alpha comes out from this linear mapping, comes out from this linear operator, and we will write alpha into L of V. And the third condition is that about third condition, we will say that every linear mapping, if we take every linear mapping or every linear operator on the zero vector, then it becomes zero vector. Okay, this is our third condition, and this is the compulsory condition for linearity or for a linear operator. Okay, this condition says that when we apply or every vector on linear operator, the third condition says that every linear mapping takes zero vector into the zero vector. Okay, this is simply means that the zero vector, the operator or linear mapping L takes zero vector into the zero vector. Okay, these are the three conditions. If we have any mapping or any function in which these three conditions are hold, then we will say that our given linear mapping or our given mapping is a linear mapping, or is a or we say that our given mapping is the linear mapping. Also, some authors introduce the linear operator or the concept of linear operator in some simple in this way. In this definition, some authors just combine these first two conditions. In first two conditions, if we combine these two conditions, then we obtain the unique condition, which is in this form, in which we say that if we multiply V1 and V2 by some scalars A and B, and then we apply the operator L, then these scalars come out from this linear operator, and the linear operator is just applied on the vectors only. And similarly the zero condition is also hold in this case. When these two conditions or these three conditions are hold in any linear mapping or in any mapping, then we say that this mapping is the linear mapping. And if any one of these three condition and these two condition is failed, then we will say that our given mapping is not a linear mapping. Next we will define the addition and scalar multiplication of two linear operators. For this we will just define the addition of two linear operator in this form: L1 plus L2. Here the L1 and L2 are the two linear operators, and V to W, and V is any vector space and W is also is any vector space. When we will apply the sum of these two linear operator in some vectors of V, then this sum of operator is just applied separately to the vector V, and we write it as L of V1 plus L of V2. And similarly we will take the scalar multiplication condition in this form. If we have some mapping alpha of L which is defined from the vector space V to W, and we write or define the scalar multiplication of linear operator in this form. Because here L is the linear operator, so we just apply L to the vector and we just take the scalars comes out from the linear operator. Now we will define some kernel and image of a linear mapping or linear operator. So here first we suppose that we have a linear mapping which is defined from a vector space V to vector space W, and we write the kernel of this linear operator or this linear mapping in this form. This is the kernel of L, and the kernel of L basically is the collection of the set of elements of V that maps into the zero vector. Actually the kernel of a linear operator is the collection of those elements which maps to the zero vector. These all the elements are belongs to the kernel of L. And similarly we define the image or range of a linear operator L, and the range or image of a linear operator is defined in this form: image of L, and the image is the set of image points, and we just simply says that the image or range is the set of image points of U. The image point or image point of U is the simply be the collection of image points. It says that the range or image space, and in symbolically we write this as if W is any vector which is belong to the vector space W, and then there exists some vector V, and we define the image of a linear space in this form: L of V is equal to W. This is the definition of a kernel and the image of a linear operator. Now we will define the dual space. The dual space be the vector space of linear operators. The dual space, actually we define some vector space to the set of real numbers, and we will denote the dual space by this notation. This is the V steric. Actually the dual space is the collection of all the linear operators. The dual space is the collection of all the linear operators. Then this type of space is known as the dual space. Now we will discuss some examples which is related to the linear operator, and the first one is the example of linear operator which is here we define a mapping of which is defined from r square to r square, and we write or define this mapping in this form, which is x1 of cos theta minus x2 of sin theta and x1 of sin theta plus x2 of cos theta. This is the output of the given mapping. So here we check that this mapping is linear operator or not, according to the value of theta. Or in other words, we just says that this mapping is the rotation, this linear operator is the rotation of the angle, and this rotation we take in the positive direction or anti-clockwise direction. Okay, in order to prove this mapping is linear or not, we just prove the three conditions of linearity, which is the first condition is the sum when we apply the linear operator L to the sum of the vector, and which is separate to the each vector, and the second condition is the scalar multiplication, and the last condition is just we check the zero vector. So in first condition, here we take the two vectors from the domain of the set, which is r square, and here we take two vectors v and w from r square, and we define these two vectors in this form, v1 and v2 and w1 and w2, and here we just check the first condition. We just check the first condition of the linear operator, and we know that the first condition of the linear operator is that the zero vector is that the linear mapping takes the zero vector into the zero vector. Okay, first we check this one. For this we just take the input of the linear operator is the zero vector, and we must be get the output is the zero vector. If this condition is not hold, then we say that our given mapping is not a linear mapping. Okay, when we substitute the zero vector here, when we substitute x1 0 and x2 0, and then you will put x1 is equal to 0 and x2 is equal to 0, and you will get the zero vector. This one is easily get the zero vector from this condition. Okay, so we say that our first condition of the zero vector is hold, and now we move toward the second condition, which is the vector addition in linear operator. Okay, so first we add these two vector v and w, and we apply the operator which we defined in the statement. Okay, when we apply the operator L from the sum of these two vectors, then it will become in this form, which is v1 plus w1 into cos theta minus v2 plus w2 into sin theta, and similarly in this form. Okay, when we simplify this expression, then we will obtain v1 cos theta minus v2 sin theta. Here we just separate the v1 vectors and v vectors and w vector. Here we just separate the v and w vectors, and when we add these two expressions, then we will get this condition. Okay, then we will easily obtain this condition. So when we separate these vector, when we separate the v vector and w vector, then we will obtain L of v plus L of w, because if you can see that this is the linear operator which is applied in the vector v, and this is the output of the mapping when we apply the operator L on w. So we easily see that, or easily prove that our second condition of the linear operator is hold. Okay, now we move towards the third condition, which is the scalar multiplication. And when we multiply the vector v by some scalar alpha, then we just multiply the scalar alpha of each term of in this operator, okay, or in this output. We just multiply each term by the scalar alpha. When we multiply each term by scalar alpha, then we will easily get this form. And after that we will just take the common of each term take the common alpha from the each term, and we will get the expression in this form, and which is the linear operator which we defined in the which is defined in the given statement, which is equal to L theta of v. So we say that the over scalar multiplication condition is also hold, and also all the conditions of the linearity is satisfied for the given operator, for the given mapping. So we say that our given mapping under the operator L of theta is the linear operator, okay, because all the conditions are hold in this one. And now we will move toward the second example, and in second example we will define a linear operator from r cube to r square, or we say that we will just define the linear operator from a three-dimensional space to two-dimensional space or plane, a two-dimensional plane, okay. And we will define this linear operator by L of x1, x2, x3 is equal to x1 and x2, and we will see that this linear operator is the projection from the points of r cube to the r square. We just say that here we take the projection of the points of space to the points in plane, okay, and we will easily prove this mapping is a linear mapping, okay. We will easily prove all the conditions of the linear operator in this mapping, okay. But here we will left the proof from you. You will easily do this one according to the example one, because this one is too much easier to, or is the proof is the simple or straightforward, so you can do this one. Now we will move toward the example 3, and the example 3 in which we will define a linear operator. We will define a mapping from r square to r cube, and we define this mapping in this form in which we just apply the operator L from the points x1 and x2, and this operator the output of this mapping is in this form, which is x1 plus x2 and 2x1 plus 2x2, and the third element of this is the x1 plus x2. And here we just check that this linear mapping is linear or not, okay. In order to prove this mapping is linear or not, we just prove the three conditions of the linearity, which we will define in the definition of the linear operator. So first we will check the zero condition, and we know that every linear mapping takes the zero vector into the zero vector. So first we check this one, and when you will substitute x1 and x2 is equal to 0 in this mapping, and you will easily get all the elements of this mapping is 0. So we say that our first condition is hold. And in second condition, actually the second condition is the vector addition, is the vector in which we apply the linear operator in the vector additions, and this in this condition the linear operator is applied separately to the each vector. So first we take the two vectors. V is the v vector is v1 and v2. The components of the w vector is the w1 and w2. And when we apply the linear operator in vector v, and we will just apply this output, and we will obtain v1 plus v2 into and 2v1 plus 2v2, and the third element is the v1 plus v2. Similarly, we will apply the linear operator in w, and we will obtain w1 plus w2 and in this form. Okay, these are the two outputs of the linear operator. When we apply L on v, then we will obtain this one, and when we will apply the linear operator L on the point w, then we will obtain the output in this form. Okay, in order to prove the second condition, we will use these two conditions. Okay, so we move toward the second condition, and which is the L of v plus w is equal to when we will add the vector at the corresponding vector of these 2 points, then we will obtain v1 plus w1 and v2 plus w2. And when we will apply this operator according to the given statement, we will obtain this one, because in our given statement the first element the first element we will get when we will add these 2 points, and the second element we will multiply each point by 2, and we add these 2 vectors, and similarly we will get the third element. This is just according to the given statement. And here now we will separate the v vector and w vector according to which steps we will do in the example 1. Okay, so here we just separate the v vectors, and in the first term and the first element, the v vectors are the v1 plus v2, and in the second the v vectors are 2v1 plus 2v2, and in third element the v vectors are v1 plus v2. And similarly we will add add and separate the elements of the w vector, elements of the w point. Okay, which we define w1 plus w2, and here the elements of and the elements of the w are the 2w1 plus 2w2, and similarly in this one we will obtain w1 plus w2, and we will easily say that this is the linear operator. This is the output when we apply the linear operator to the point v, and this is the output when we will apply the operator L from the point w. Okay, here we see that our second condition of the linearity property is hold. And now we will move towards the third condition of the linear operator, and which is the scalar multiplication condition. And when we will apply alpha to the vector v, and then we will apply each element of the output to alpha. Okay, after that we will take common of each term in this output, and we will obtain the output in this form, and which is v1 plus v2 into 2v1 plus 2v2 and v1 plus v2, and we easily say that this output is equal to L of v. Okay, in this example we will also see that all the conditions of the linear operator are hold, so we say that our given mapping is the linear mapping. Now we will discuss some examples in which we show that our given mapping is not a linear mapping. Okay, in this example we will check the first condition, which is the zero vector condition. Okay, when we will apply, or we will take the zero vector in this form, and here when we will take the x and y is equal to 0, then you get, when we put x equal to 0 here, then you get 0 plus 3, and which is 3, and when we put y is equal to 0, then you will get 0, and when you put x is equal to 0 and y is equal to 0, then you will obtain 0 vector. Okay, and here you see that when we will take the 0 vector, then we cannot obtain the output is the 0 vector, because this output is a non-zero vector. Okay, or non-zero point. So we say that the 0 vector is cannot take the 0 vector. So we say that our first condition is our first condition of the linear operator is fails. So we say that this mapping is not a linear mapping. Okay. Also we will define some other mapping which is in this form, and which is f of x, y, z, and we define this mapping from r cube to r square in this form, and which is x mod into y plus z. And here when you can check the zero vector, then you will easily obtain the 0 vector. When you put x is equal to 0, y is equal to 0, and z is equal to 0, then you will obtain the 0 vector. So we say that our first condition or 0 vector condition is hold in this one, and similarly our second condition which is the vector addition condition is also hold in this one, and we now apply the we now check the third condition of the linear operator, and which is the scalar multiplication condition. And we see that the third condition, which is scalar multiplication condition, is not hold here. So we say that our given mapping is not a linear mapping. But now we will check why our third condition is not hold, and so we will prove this example by taking some particular point in the space or particular point in r cube. When we take v is equal to 1, 2, 3, and when we take any scalar which is a negative scalar, and when you multiply k by v vector, then you will get -3, -6, and -9. You just multiply this scalar in each element of this point, and you will get this one. Okay, and when we will apply the operator f in this v vector, then you will get 1 and 5. So you will apply this one. Okay, when you will take x by 1, y by 2, and z by 3, you just put x1, y2, z3 in this point. Okay, when you put x is equal to 1, and the mod of 1 is 1, which is this one, and when you put y is equal to 2 and z is equal to 3, you will get 2 plus 3 5, which is this one. Okay, this is the output of f of v. And when we multiply this output by k, and we suppose that the value of k is -3, and when you multiply the -3 here, and you will obtain -3 into -15, this order pair. You will obtain this order pair, and we will just take the equation number 1. We will just named as the equation number 1, and now we will apply f to the scalar multiplication of the kv, and then we already defined the product of k and v. The product of k and v is the -3, -6, and -9, and we just put here -3, -6, and -9. And when you will apply this operator f, when you apply this operator on 3 points, then you will get x mod y plus z. Okay, when you apply f on these 3 conditions, you will take the mod of the first element, because here you take the mod of first element x, and when you take the mod of -3, and you know that the mod of -3 is the +3, so we obtain the +3, and in the second vector we just add y and z, and you just add these 2 vectors, and when you add -6 and -9, you will get -15. And here you clearly see that the equation number 1 and equation number 2 is not equal, because this is our third condition of the linearity property. And here we see that f of kv is not equal to k into f of v. So we say that our third condition of the linearity is not hold. So we say that f is not a linear mapping. Now we will move towards the example number 4, and the example number 4, here we just define the linear operator. We define the differentiation of a linear operator. Okay, the differentiation is a linear operator which is maps n times differentiable functions into the n minus 1 time differentiable function. Okay, you know that when we take a derivative of any function which raise it is decrease the power, it is decrease the power of that function. Okay, when we take the differential operator of the n time differentiable function, okay, the Cn of AB be the n time differentiable function, and D is the differential operator, which we also denote this differential operator by capital D, and this differential operator, when we apply this differential operator to the n times differentiable functions, then you will obtain the output of n minus 1 times differentiable function. Okay, and similarly in example number 5, we define the Cauchy's law. Okay, the example number 5 actually be the Cauchy's law. The Cauchy's law states that the force on a surface at a point is equal to the stress tensor normal to the point. This condition is known as the Cauchy's law. Okay, and mathematically we will write this condition by F is equal to tau of n. Okay, in mathematically we write just this force F is equal to some tau of n. Okay, and here the F is the force of the area, and the point n is the outward normal, and tau be the linear operator. Okay, we will define these operators in this point, and here F be the force on the surface, and n be the normal on that point. Okay, so the tau is the linear operator, and we will define this condition as F is equal to tau of n. Now we will also define the Cauchy's law in the Cartesian system. The Cauchy's law in the Cartesian system in this form, which is the f of x, f of y, and f of z, which is the partial derivative with respect to x, y, and z, and we will take and we will get some this matrix is equal to some in the matrix of 3 by 3 form, and which is the tau of x, the second derivative of tau of x, and the second derivative of x and y, and which is the second derivative of tau with respect to x and z, and similarly we will get the second derivative of y and x, second derivative of y and z, and similarly the derivative of tau with respect to z and x, and z and y and z, and we will multiply the derivative of outward normal with respect to x, y, and z. Okay, this form be the Cartesian form of the Cauchy's law. Okay, now we will discuss the definition of derivative and the integral mapping. As we already discussed the condition of the derivative mapping in the previous example, and now we will again discuss the condition of the derivative and the integral mapping. So in order to discuss the derivative condition, we just here apply the two conditions of the linear operator in the differential form, and we already know that when we apply the derivative of the sum of two vectors, then derivative applied separately to the each vector, and similarly when some scalar is multiplied by the vector and we take the derivative, then this scalar comes out from the derivative sign, and we write in this form k into du over dt, and And similarly we denote the integral operator by j, and the integral operator with the j is defined from V to R be an integral mapping, and we say that the integral mapping, and we define this mapping in this form j of ft. Here f is a function which is lies in the vector v, and we define the integral operator from 0 to 1 into f of t and dt. And similarly we will define the two conditions of the linear operator in the integral form, and here we already know about these two conditions. When we take the integral of the sum of two vectors, then we will apply this integral to separate of the vectors, which is in this form 0 to 1 u of t n plus 0 to 1 v of t. And similarly when we multiply some vector u by k, and we take the integral, then the scalar k comes out from the integral sign, and we will write in this form, which is k into 0 to 1 u of t and dt. In today's session we will discuss all the linear operators. We will discuss some examples of the linear operator, which is differential, integral linear operator, and the rotation and the linear operator which is defined by the rotation of the angle theta. This is our today lecture, and thank you so much for watching.